Thank you. And can I have the pointer? Oh, thanks. Okay. So thank you so much for the invitation, and thanks you to organizer for bringing back to Seoul, which is a city that I love. And this is a work that I think the title changed a little bit, but nevertheless, it's Bootstrap meeting the real world, so no worries. It's work in collaboration with Miguel Correa and Alessandro Giorgudis, which are in this picture and also in the audience, I guess, somewhere. And okay, it appeared recently last week. So let me start by reminding you something about the QCD triangle. So why we get the triangle? Because we have two variables, two limits, and one relation, okay? And in this conference, we already heard a lot about the regime in which the kinematical invariants SNT are very large. This is the hard scattering regime, corresponds to asymptotic freedom, and in this conference, we hear a lot about this. There is another regime in which SNT are order 1, which is the confinement regime, and in this regime, we have like, well, KPT or unitarized version of kernel perturbation theory, lattice, and S-matrix bootstrap recently. But then there is a corner where S is very large and T is order 1, which is the forward scattering region, where we only have like Regge models, and it's very hard to study. And in this talk, I will try to say something about this region using the bootstrap. Let me remind you why we need Regge theory. So we observed experimentally back in the days that there are a lot of resonances showing up in a scattering amplitude in QCD. And for each of these resonances, we can write an exchange diagram, which we exchange like a part with some spin J. And this would grow violating unitarity or causality, if you want. And to cure this problem, it has been introduced this Regge behavior, in which you make the spin basically scale with T. And this leads to a cross-section which is grows according to causality and unitarity. Doesn't violate any bound. The fact that this trajectory intercept at 0.55 tells you the cross-section must decay. And this was very nicely observed in the past and was a success of Regge theory. But later, people discovered that actually the cross-section rise. And this gave rise to a conundrum that has been solved by the introduction of a new trajectory, which is the Pomeron trajectory in QCD, okay? Which is like this trajectory intersects at some point, 1.08, and explain this growth. So it's like one of the success of Regge theory, as I learned from Miguel, probably. And what are the experimental evidence of the Pomeron? So far it was like a very involved argument. The experimental evidence comes from the fact that if one writes the differential cross-section in T, which is just the amplitude square divided by a square, and use the Regge behavior, then it will decay exponentially with T, with a prefactor which is called the B of S, is this function, that grows with S. So it decays faster as it decays exponentially faster as S increases. And this is called the shrinkage of the diffractive cone, which is like an effect that has been measured in the past, and people fitted also the slope of this Pomeron trajectory. And today we know that also like there is some deviation from some square root of S transient behavior. So it's really, we believe it's really a log. So it's like experimental evidence of this trajectory. So another success. And then the most brilliant result, I think, is the Froissart bound, which tells you, and is all related to this question, which tells you that this total cross-section, which probably you heard last week in the school from Aninda, is bounded by the log square of S, with some factor, which is 4 pi, the strong coupling in EFT, as we learned this morning, and T naught, which is like some scale. Now, if you take seriously this formula, you will see the amplitude will grow like S log square of S with an intercept which is 1. And this is in tension with what I told you 1 second ago, that the intercept of the Pomeron is 1.08. And also there is the well-known fact that there is an experimental gap between the cross-section 14 TV at LHC, like 0.27 millibar, and the bound, if you take it serious, it gives like 60 millibar. So it's like very large. And still now we ask a question like, okay, but Froissart bound is asymptotic, is 14 TV large enough to explain these things? Is the bound optimal? What is this S naught, which is some arbitrary scale? So in this paper, we try to make some progress on these questions. And let me already anticipate the main results so that you can decouple and sleep if you're jet lagged, but just to state at the beginning what are the results. So the main result is that we obtain an absolute bound on the average cross-section, which does not depend on any arbitrary constant. So the average cross-section is the average of the cross-section up to some energy S. So for each S, we get a bound, which we can plot here, and there is no ambiguity in this bound. And one teaser for future, let's say, applications, is that if we assume that at 14V, spin effects in protons decouple, and pion exchange is irrelevant, then we actually get a bound that is not that bad. It's just a factor 10 away from the experimental cross-section. Of course, this is not completely rigorous, just suggestive. But we believe it goes in the right direction. This is one result. The second result is that with the bootstrap, we are able to construct amplitudes, as I will explain in a second, and we conjecture that the amplitude maximize the interaction strength at all energy scale, which seemingly will saturate the Frost bound, lies at a special corner in the space of amplitudes. And it's this corner here. Okay, so space of 4D amplitudes, and this is like the corner. The axis, if you want, is lambda phi to the 4, and d4 are to the 4 directions. And we construct this partial amplitude with the bootstrap. We study the properties, all these peaks, we understand the spectrum, and so on. So I will try to tell you something about this. Now, let me make a pause and explain a little bit. So we heard already a lot about bootstrap, simple bootstrap, and so on. So let me explain what we do. Our approach, it's called bootstrap, but let's say more physically should be intended as like an effective S-matrix approach. Because what we do is that we construct the most general function satisfying analyticity crossing a unitarity. And this is not very different than effective field theory paradigm. Because you see, in the FT, we write a Lagrangian, and then use perturbation theory to systematically compute our answer. And in this S-matrix, effective S-matrix approach, we write an ansatz and use optimization theory and semi-definite programming to get the answer. And that's why it's called bootstrap. There are some good news and bad news. Good news is that it's non-perturbative. So ideal for strongly coupled system, QCD, or integral models, as Lucy, I think, will talk in a couple of days. But it's not systematic because it's hard to include multi-particles, for instance. Although there's been some recent progress, and Alexandre will explain something in next talk, and also recently by Cliff and Grant Raman. But what the S-matrix can do, so let me show you two examples that are very diverse, that show the versatility of this method, let's say. So it can derive universal bounds on Wilson coefficient and construct amplitudes. And one example is related to supergravity effective field theory Wilson coefficients. So you have gravity, you add the first correction, r to the 4, and then you ask, what's the bound on this coefficient? And with the bootstrap tells you the bound is strictly positive, and then you compare it with string theory, you get some bound that is close to non-perturbative string or M theory, for instance. And the second is about constructing amplitudes. An example is pi-pi scattering, which recently we managed to basically construct an amplitude that accommodates the known QCD spectrum, and we are also able to predict the tetraquark. It was to be my original talk, but then this paper came out and I decided to switch, but I wanted to mention that we have this interesting prediction is being checked by LHCb. So these were two regimes that we know very much about. So in this talk, I wanted to start to make some steps and study also this forward soft QCD. Okay. Now, before going to the main theme of the talk, let me explain in pills what is the primal strategy that we adopt, how it works. So consider the theory of a gapped scalar phi of mass m equals to 1 in 3 + 1 dimensions. Very simple. Then we write an ansatz, which is manifestly crossing symmetric. You see, it's a sum over a plus b plus c smaller or equal than n. There is some free coefficients, rho s to the a, rho t to the b, rho u to the c. If alpha abc is crossing symmetric, this expression is crossing symmetric in s, t, and u. Then rho, it's a conformal mapping from the cut plane to the unit disk. Therefore, this is just an expansion in the product of 3 disks. And it's just the most general expansion analytic function, all Mandelstam invariants with correct cuts. So crossing and maximum analyticity are encoded in this ansatz. What is not is unitarity. Second step, we take this expression, we plug it into the definition of the partial S matrices, where there is just a Legendre polynomial, T. We replace it in terms of the scattering angle, we integrate in the scattering angle. And then we basically decide what is our observable that we want to bound. We maximize our observable given the unitary constraints, which acts on these partial S matrices that tells you probability must be small or equal than 1 for all spin and all energies. And we like to cast this into semi-definite positive matrix. That's why we use the bootstrap and SDPB. And we bound basically for all spins up to some L. And then we have to take limits, because we want these answers n go to infinity and span all possible functions. And we want to send number of constraints to infinity so that we are sure that we bound all the unitarity. So this is the primal strategy. Now let me go to the, let's say, to the main part of the talk. So we bound this average cross-section, which is, again, this integral from 4 to S of the sigma dot with some irrelevant prefactor. Now, this is the most technical slide, so bear with me a second. So the strategy that we adopt as a part analytic and a part numerics. So we first expand in partial wave the cross-section inside the integral. So you see there is the integral, there is a sum, there is some S matrices, some just factors, and we split the sum into low energy and high energy. And this is like common in the proof of the Schwarzschild bound. Then the low energy part, we bound it using unitarity that tells you that 1 minus the real part of the S matrix is more equal than 2. We get a number that scales like L squared in D equals to 4. Okay, this spin L is totally arbitrary, so we split the sum at some arbitrary point. Then for the higher spin part, it's a bit harder, so I have to introduce some additional observables. One observable is the second derivative of the amplitude, which is positive and bounded. You can choose other observables. This was our choice. And this derivative of the amplitude is dispersive, can be written as an integral, and it's positive. So what you can do is that infinity here, you can replace it with S so that it mimics this integral. The sum, you can make it start from L so that it mimics this sum. And then you basically get that this second derivative is bigger or equal than some prefactor times the high spin contribution. So you invert the inequality and you get equality on the higher spin contribution. And the main thing that we could do is that we can bound this derivative with the S matrix bootstrap. So it's like a numerical input. So let me write the final function that we get with this simple splitting. So you get the sigma bar dot, the average cross-section is more equal than some factor with the Pochhammer, plus this contribution with this second derivative C2 divided by the Legendre polynomial. And this bound is valid for any spin L that we choose to split and any T naught, which is some momentum transfer, Euclidean momentum transfer. And that's it. This is like the whole formula that bounds the average cross-section. Now, C2, you can get it from this plot. This is obtained using the bootstrap. You can plug it in this formula, and then you can play. You can ask what is the optimal bound. Okay, so this is what we did. And if we take the S that goes to infinity limit, then we get the spin scale with the log of S, and we recover the original Schwarzschild bound in the dimensions, the one that I showed at the beginning. So this formula is compatible. Now, what we can do is to also maximize directly the cross-section, the average cross-section. So that was like a bound that combines analytic inequalities and numerics. And now we can bound it directly. And if I bound it directly, what I get is that for each value of S, so for each energy I decide to smear, I get these numbers. So you see, all is below these points is included. This is rigorously excluded by our inequality. And what is in the middle, it's some gap that is due to crossing, if you want. So you see, crossing improves by factor 5 over the improved version of the Schwarzschild bound that we derived. The primal bound grows slowly. And for each S, we can also construct the optimal bound, so we can study its properties, which I will skip over because time is running out. Okay, so I can also study the property. But the thing is that we can solve an optimization problem for each S where we smear the cross-section and maximize this quantity and construct the amplitude. But the question then is, what happens if I take the limit of S that goes to infinity and I consider the strongest interacting amplitude in 4 dimensions at all energy scales? So this is like the relevant question. And we conjecture that the Froissart, we call it Froissart amplitude, we conjecture that lives at the kink of the allowed space of all possible amplitudes. And the reason is because when we maximize up to some energy S, we can compute the amplitude. We can extract these 2 coefficients, which are just the coupling in lambda phi to the 4 and d4 phi to the 4, if you want. And we can draw a trajectory in this space. And then you see from 20 to 30, we go here, 30 to 40, we go here, and then you follow ta, 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 and then you conjecture that goes to the kink. That's basically how it works. We have more arguments, but this is how you can see it. So we study the amplitude at this kink. And now let me tell you a few properties about this amplitude. So this amplitude at the kink should be the amplitude that maximizes the cross-section at all energy scales. And the usual Froissart bound, if you want a picture, opla. Yeah, this I didn't want to show anyway. The usual Froissart bound picture is that it should look like more a black disk. Okay, so as you go to high energy, you basically in a disk absorb everything. So we can try to do some analysis and look at the profile of our amplitude, the conjecture is the one that maximizes the cross-section, in energy and impact parameter. And here the black region is where you transmit, and the white region is where you reflect. And then you see that for each S, there is a small region, annular region here, that basically the amplitude is reflecting. And the nerd inside me could not waste this opportunity to throw this joke or, well, you know, basically we find that the amplitude that maximizes the cross-section is more like a ring. Okay, so that's the one that governs the cross-section. So this white ring model has like a radius R1 and a radius R2. Okay, so like some simple profile. And from this simple profile, you can plug it into the impact parameter formula and derive some expression for this white ring model. Okay, so now we are just trying to model. We say, okay, we observe this feature. Let's write model, analytic model. Let's plug it. Let's see what amplitude we get analytically. And the amplitude you get is some difference of Bessel function with S divided by the square root of minus t. And this is like some simple exercise. And now in the last few slides, I will just show how this simple picture is compatible with many of the properties that we can extract from this amplitude. So the first is the Pomeron that I mentioned at the beginning. So is there a Pomeron here? There is, because you see that the bootstrap answer, this is, for instance, the differential cross-section at 2 different S. This is like S equals 50, S equals 200, so increasing S. And at small t, there is some linear behavior and then it deviates, so the Pomeron dominates in the forward limit. But then if we go to finite t, there is a diffractive pattern that emerges out of this amplitude. So you see the solid line is the bootstrap, and you see how it decays and then jumps, and there are these rings. And the white ring model captures very nicely the position of these rings, although these are really nodes for this function, while our function doesn't go to 0 at these dips. So what would this picture predict? And this picture, so what does it predict? Imagine, for instance, that the cross-section, this white ring model, grows like 4 pi big radius square minus small radius square. So it looks like Froissart. For instance, if we take that big radius, goes like some R0 log of S, you get Froissart growth. But then you can compare the large S limit fixed t of this Bessel function, which is just this Bessel function here. And you can compare it with the Sommerfeld-Watson representation to extract the behavior of the partial waves in t, the complex partial waves in t. So you compare these two expressions, and what you get is this answer, which is that you have a function that is like 1 over this denominator. Okay? And this denominator is very interesting because this is not a pole, it's a branch cut. So this white ring model right away produces what people called in the past some Regge cut that extends from 1 plus minus r naught square root of t. And you see it would be real for t positive, but then it would become imaginary for t negative. And here at 1, there is like a triple pole, which is compatible with some claims in the past about the Frossard growth. So can we see some features in our amplitude like this? The answer is more or less, and I will show in a second. And so, so this is the answer. So let me decode it a little bit. So this is the full spectrum of this function that we extract, which is very complicated. And how we get it? Well, we basically project to complex spin our function. So we take our function, take this continuity in T, we integrate with the Legendre of second kind, and this depends analytically on L, so we get the partial wave for each L. So for each L, we can look for resonances in the complex plane, and we can plot the spectrum. And the spectrum arranges nicely in a Chu-Frauchi plot, but it's very rich. And you see that we can identify at least 8 trajectories asymptotically that we give names. And the interesting part is that some trajectories correspond to physical observable peaks in the cross-section, like this A1. This would be like some more natural Regge trajectory. And some of them are what you would call subleading trajectories. And there's some weird stuff on the left. Some trajectories intersect the t equal to 0 axis, so they correspond to the Pomeron, for instance. They correspond to this trajectory that dominates the energy behavior. And you see there is a trajectory that more or less goes like 1.15, the intercept, and it's subleading compared to the leading. And then we get many trajectories, and one of them has some sort of infinite slope. So you see the white ring model was predicting some Regge cut, some weird square root, and we also observe some square root behavior. But we also have many trajectories on the left which have this square root behavior. And this we don't know, actually, any model that features these things, and this is like some open question. So let me conclude. So we have derived absolute bounds of the average cross-section, finite energy, that do not depend on any parameter, are totally model independent. And we conjecture that the Frossard, the amplitude that has the maximal growth in 4 dimensions live at the king of this space. And this Frossard amplitude is a rich spectrum of resonances. The question is like, are all these resonances necessary? So can they be constrained from first principles? And let me conclude by saying that, okay, this was just a game, in the sense it's just some scalar amplitude in 4 dimensions. It would be cool to add more assumptions in the UV and focus more on proton-proton scattering, or maybe scatter fermions would be better than scalars, for instance. And it would be nice to compare these plots that we get to the actually plots that people measure at LHC, where they show this basically this exponential decay of the differential cross-section, and then they show this ring structure, this dip, and then decays again, maybe there is a second dip. And we could predict it, perhaps. And I will stop here and leave with a quote from Frauch a long time ago, that he was saying something about nonlinear trajectories we observed that are not totally crazy. So I will stop here.